Hello everyone, my name is Svyatoslav Gryaznov, and I'll be presenting our joint work with Pavel Pudlak and Navi Talbanfard that's called Linear Branching Programs and Directional Affine Extractors. So let us start by defining what a branching program is. It is a way of computing Boolean functions that is represented as a directed acyclic graph that has exactly one source and exactly two targets. The targets are labeled with 0 and 1, and it calls the value of the function. And every inner node of this program is labeled with some variable like x1, x2, x3 here. And from every inner node, there are two outgoing edges labeled with 0 and 1. And for 0 edges, I will use these dashed lines, and for ones, I will use these straight lines. And a branching program is a read once if on every path from the source to a target, each variable is queried at most once. So the program on the left is read once. Another important mode of computation for Boolean functions is parity decision trees. And in this case, our program has to be a tree, not just a deck. However, we can query linear forms now, not just variables. And it is very natural to try to combine these two definitions together. And for this, we suggest linear branching programs, a model that is a branching program, but with linear queries instead of querying just a variable. So on the left, you can see the linear branching program equivalent to a parity decision tree from the previous slide. So a natural question is, can we prove some lower bounds on this model? Or maybe can we prove lower bounds and some restrictions of this model? And in particular, whether we can define some analog of this advanced property for usual branching programs to our case of linear branching programs. It turns out that the answer is mostly positive, but first let us discuss some issues that can arrive when we try to define this advanced property. So one important property of usual branching programs, usual advanced branching programs, is the following. If we consider any inner node V, and we consider the subprogram rooted at V, then regardless of what path we chose to arrive to V, so we can arrive to the left or to the right, then this subprogram will compute the same Boolean function. And if we consider a naive way of defining advanced property for linear branching programs, that is, for every path from the source to a sink will require our program to have independent queries, then unfortunately this property doesn't hold in this case, and it is kind of crucial for the analysis. So to overcome this issue, we suggest two different definitions of read once property for linear branching programs, and let's define them now. So let's define by pre of V the span of all the queries above that appear on any path that leads to this node V. So it is in orange on the left. And similarly, by post of V, we define the span of all the queries that appear below V, and including the query at V. So it's the span of all the queries that can appear in the subprogram rooted at V. So our first definition of read once property is the following. These programs are called weakly read once linear branching programs, and we require that for every inner node V with a query Q, we require that Q does not belong to this pre of V. And another definition is strongly advanced linear branching programs. We require an even stronger assumption that for every node V, these spaces pre of V and post of V have a trivial intersection, so they only have 0 in the intersection. In what follows, we'll prove an explicit constructions of strongly advanced linear branching programs and some applications of this construction. And in the last part of the talk, we'll outline the connection of weakly advanced linear branching programs to proof complexity and say why this weakly advanced definition is important. But first, let us recall how the argument of proving lower bounds for usual read once branching programs is carried out. So let f be a Boolean function, and this function, the function f is demixed if for every subset of indices I that is not too large, so its size is at most n minus d, and every two distinct partial assignments sigma and tau with the same domain I, it holds that f restricted to sigma and f restricted to tau are different functions. For our applications, we need a bit different but equivalent definition of demixedness, and that is for every partial assignment sigma of size at most n minus d, and every vector c with support of c that lies in the domain of sigma, we require that there exists x consistent with sigma such that f of x is not equal to f of x plus c. So it is rather clear why these definitions are equivalent, but this second one is easier to work with, and it's easier to generalize for our linear branching programs. An important result about mixed functions is that any demixed function requires branching program, read-once branching program of size at least 2 to the n d minus 1. So they have the exponential in n minus d. So for our linear branching programs, we generalize the definition and introduce affine mixed functions. So again, let f be a Boolean function, and f is the affine mixed if for every affine subspace S, which consists of a vector space V shifted by vector A, and dimension of S is at least D, and for every vector C that does not belong to this vector space V, we require that there exists X in S such that f of x doesn't equal to f of x plus c. And our result about these affine mixed functions is basically equivalent to the one about mixed functions, and that is any affine mixed function requires strongly read-once linear branching programs of size at least 2 to the n minus d minus 1. So how do we construct these affine mixed functions? And for this, first we need to recall some properties of affine extractors. So again, let f be a Boolean function, and the bias of f restricted to a set S is defined as the following. It is the absolute value of the expected value of -1 to the f of x, where x is chosen uniformly on S, and it is said that f is an affine extractor for dimension d with bias epsilon, if for every affine subspace S with dimension d, the bias is limited by epsilon. For example, the inner product function, the usual Boolean inner product where the input is split into two equal parts of size n over 2, and defined as following, is an affine extractor for dimension n over 2 plus k with bias 2 to the minus k. So for our application, we introduce a generalization of affine extractors. So f again is a Boolean function, and we consider a functional derivative of f in the direction a. Well, a is obviously not zero. So it is a function daf of x, that is a function derivative. And f is directional affine disperser or extractor for dimension d or for dimension d with bias epsilon in case of extractor, if for every non-zero direction a, this function daf is an affine disperser or extractor with appropriate parameters. And it is clear that a directional affine disperser for dimension d is the affine mixed function. So for our theorems, for our applications, it is enough to provide a construction of directional affine dispersers. So to do this, we start by recalling what the trace map is. So we consider the trace map between the fields f2 to the n and f2. And for these fields, it looks like this. It's the sum of x to the powers of 2. One property of trace that we need is that it is a f2 linear function. And since in our applications we work with Boolean fields, with Boolean cubes instead of these fields of prime power size, we'll fix for the rest of the talk the f2 linear isomorphism phi between the Boolean cube and the appropriate finite field of the appropriate size. And another important property of the trace map is that the set of all linear Boolean functions coincide with a set of functions that has this form. It's the trace of some parameter mu multiplied by phi of x. And mu is any element of the field f2 to the n. We also need the class of Boolean functions called band functions. So f is a Boolean function and f is band if its Fourier coefficients have the same absolute value. So the Fourier spectrum has the same magnitude. And intuitively, one can think about band functions as the most nonlinear functions. And for example, the inner product function is band. And even more, it is a rather well-known fact that any band function is actually an affine extractor for dimension n over 2 plus k with bias 2 to the minus k. It is relatively well known, but one can refer to one of the sources for the proof. However, for our applications, the inner product function is not really suitable, but we can define a very similar thing, a very similar function that works for us, and is defined as following. So we split input into two equal parts of size n over 2, and then we take trace of the multiplication of phi of x and phi of y. And this function g that we defined is band, thus a good extractor for this dimension over 2 plus k with bias 2 to minus k. And this function actually behaves very similarly to inner product, but for these fields of size of power of 2. So we finally have all the components we need to construct our directional affine extractor. And we define the function f, where we split our input into 3 equal parts of size n over 3, and define the function f of x by z as the trace of this product f phi of x times phi of y times phi of z. And I want to state and sketch the proof of this theorem, that f is a directional affine extractor for dimension 2n over 3 plus k with bias 2 to the minus k. So the proof sketch is the following. If we just write down the functional derivative of f, then we can use the linearity of trace and phi, and this cubic part will cancel itself out, and what we'll have is that we'll have the trace of some degree 2 polynomial of these three variables, phi of x, phi of y, phi of z. Then, since our shift is non-zero, we can fix one of these components x, y, or z some fixed value, like for example, let's just fix z to some value z0, and we can do it by decreasing our dimension. So if our dimension was 2n over 3 plus k, then we will something then it decrease by n over 3, since we fixed only one variable, and we'll have something like n over 3 plus k. But after this substitution, our function will depend only on two variables, and it will look like trace of some degree 2 polynomial of two variables. And this function is band by basically the same argument as the function g from the previous slide is band. So then you can just apply this property of band functions, and that concludes the proof. So our construction of directional affine extractors is actually even stronger than we need. For applications, we really needed only directional affine dispersers or even simpler functions. But this extractor property allows us to prove even stronger bounds, and that is average case Lauer bounds instead of just the worst case Lauer bounds as previously. This goes along with the work by Cohen and Shinkar, where they prove this average case Lauer bound for parity decision trees. So if f is an affine extractor for dimension d with bias epsilon, then for every function g that's computed by a small parity decision tree, and by small, it means that its size at most epsilon times 2 to the n minus d, it holds that the distance between f and g is almost maximal. It's almost 1 over 2. So it's like 1 over 2 minus something of epsilon. And our analog of the theorem is the following result. if f is now a directional affine extractor for dimension d with bias epsilon, then for every function, Boolean function g, that is computed by a strongly advanced linear branching program of size at most epsilon times 2 to the n minus d minus 1, so they're computed by small branching programs, it holds that distances again very close to 1 over 2, but the convergence rate here is something like square root of epsilon, but it's not really important if epsilon is exponentially small. I want to sketch the proof of this theorem, and for this we need the definition of full advanced branching programs. So we say that a advanced linear branching program is full if for every inner node V, the space, the query spaces on any path that leads to V is the same. And important property of this these full programs is that if we have some advanced branching program, whether it's weakly advanced or strongly advanced, and it has size s and n variables, then we can translate it into equivalent one of size 3n over 3n times s. So it's only a linear blow up, but our resulting program will be full. So the idea behind this transformation is the following. So suppose we have this linear branching program on the left. It's obviously not full, since we even have different number of queries on the left and right path leading to V. But we can try to translate it into a full program, and we can do it by adding this dummy node with this redundant query, where we just query something and then just ignore the value, since the outgoing edges lead to the same node. But after the transformation, this program is now full. And we can actually apply this idea inductively starting from root and prove the second bullet point above. So let us describe the proof of this theorem. So we start by replacing the program with an equivalent full program, and we also imply some additional property that every path must have length at least n minus d. We can again do this by adding these redundant queries at the end, and it will not really increase the size. It doesn't significantly increase the size, and it will be quite safe operation. And then we can observe that if a lot of different paths meet the same inner node, then it is actually the case that a lot of wrong inputs has to pass through this node. And by wrong inputs, I mean the inputs for which the functions f and g differ. And since we want to give a lower bound on the distance between f and g, we actually want to give the lower bound on this number of wrong inputs. So in particular, if our inner node V has depth n minus d, and k paths pass through this node V, then the number of wrong inputs is at least this function. It's something linear in k minus something of square root of k. And then we can use the fact that our program for function g is small, is size limited by the statement of the theorem, and also we use this property that all our paths have length at least n minus d. So we have 2 to the n minus d paths in total if we consider vertices at depth exactly n minus d. So we can just sum over all such vertices and then apply something like Jensen inequality and derive with the statement of the theorem, which will conclude the proof. So lastly, I want to discuss the connection of these three advanced linear branching programs to proof complexity, and also say why this weakly advanced branching program definition is important. For this, we need to say how we define branching programs for relations, not for Boolean functions. So let us consider a concrete relation search f, that is a search clause problem, where we are given an unsatisfiable CNF formula f, and we want to know what clauses are falsified by given assignment to the variables of f. So our things now clauses not just values of 0 or 1, as for Boolean case, but everything else is basically the same. And we also need this proof system called RESC-XOR proof system. It is an extension of resolution, the standard resolution proof system, with linear equations over F2. So instead of just using variables as literals, we can use linear forms over F2 as literals. As usual, RESC-XOR system is tree-like. If refutation is tree-like, if you can arrange the proof as a tree. And Itzikson and Sokolov has this result that connects parity decision trees and tree-like RESC-XOR refutations. So every tree-like RESC-XOR refutation can be translated into a corresponding parity decision tree for this search clause problem search F without an increase in size. And the opposite direction also holds, is that if we have a parity decision tree for the search clause problem search F, then we can translate it back into a tree-like RESC-XOR refutation, and size will increase only with some constant factor. We want, and we actually define a similar thing for our weakly advanced programs, but first we need to say what it means that we need to define what a regular RESC-XOR refutation is. So we say that RESC-XOR refutation is regular or weakly regular if for every clause C of in our program that is obtained by the application of the resolution rule on some literal Q, we require that the span of all the queries that appear in the applications of other resolution rules to which involve C or something that was derived from C requires that the span does not contain Q. So in other words, if we use Q to derive C, then we cannot use Q afterwards at all. If we when we use something like C or something that was derived from C. So our result that connects this regular RESC-XOR refutation and weakly advanced programs is the following. The first point is basically the same, and that is every regular RESC-XOR refutation can be translated into the corresponding weakly advanced program without the increase in size. And the a bit more interesting property is the second, and that is every weakly advanced branching program for this search clause problem search F can be translated into a regular RESC-XOR refutation of size big O of ns. So we have this linear factor, but it's not really important if our S is superlinear. So finally, let me outline some open problems that we consider interesting in this direction. So the first one is coming up with some explicit constructions for beta dimensions. So we proved our explicit construction for dimension to n over 3 plus something, and ideally we want it for sublinear dimension or even for logarithmic dimension, which will be the best possible result. Also, our construction only works for strongly advanced branching programs, and we described why these weakly advanced branching programs are important and how they connect to proof complexity. And for this, it will be interesting to prove some lower bounds, like forced case or average case lower bounds on these weakly advanced branching programs for the Boolean case. And lastly, the proof complexity direction also needs investigation, since our results only hold for now for functions. And for this search clause problem, it becomes a bit more complicated. So we want to have some results about the search clause problem for maybe even for strongly advanced branching programs, but for the search clause problem. And that's it. Thank you for listening.